I will begin with some definition and the goal of my lectures, and then I will speak about the topological dynamics of these flows, and then the main part will be about ergodic theory, ergodic theoretical properties of these two flows. Most of the definition were given by Frédéric or Jean-François, but I will recall them just because I don't have the same notations. So the hyperbolic half plane is the upper half plane endowed with the metric if you have a point x plus y, iy, and a vector v making an angle theta with the horizontal. The metric, the hyperbolic norm of v will be the Euclidean. Oh, no, I don't want to. Okay, the metric. Okay, again, the hyperbolic metric is dx x dy over y square. Okay. The hyperbolic half plane is good to do computations, but to do pictures, it's better to work in the hyperbolic disk and endowed with a metric that I don't want to write, because you don't have to do any computation on the disk, and you have to use the map. It should be this one. In one direction it should work, to send the hyperbolic half plane to the hyperbolic disk. I would like to mention in the introduction that I will speak about geodesic and horocycle flows on these hyperbolic hyperbolic surfaces, but I will try to give you arguments that are at the most general possible, and the most argument will work in variable negative curvature and in higher dimension, and even some of them in non-positive curvature. And I could also say at the very beginning that a lot of arguments are inspired by works of Yves Coudin, even if the historical results are not due to him. So what are geodesics? Geodesics are, okay, half circle orthogonal to the boundary, or here, like that. And horocycles are circles or tangent to the boundary, and so orthogonal to geodesics. And here you have horocycles. And okay, this picture is very important. In fact, the geodesic and horocycles are defined here on the hyperbolic plane, but the geodesic and horocycle flows will live on the unit tangent bundle of the hyperbolic plane. And so first, let me recall that the PSL2R acts is a group of positive isometries of H. It acts by homographies, and it acts, so this group of isometries acts simply transitively on the unit tangent bundle. It means that given any two unit vectors, V and W, there exists a unique isometry gamma which sends the base point of V to the base point of W and the direction of V to the direction of W. And so then it's immediate to identify this space with PSL2R, and the classical way, take the point I and the unit vertical vector that I will call V0, and if you have a matrix G, an element G in PSL2R, you associate to it G times V0, and this allows the identification between the two spaces. And now I will speak about geodesic and Horocycle flows. So take a vector V and consider the geodesic that it defines. And the geodesic flow, I have two flows, so I will not call it phi, but G. So G for geodesic and H for Horocycle. So the geodesic flow will move the vectors along the geodesic that it defines. So if you have a vector V, the geodesic flow at time t moves the vector from a distance t along this geodesic. And the Horocycle flow oh, no, Horocycle were yellow, but okay. The Horocycle flow moves the vector V from a distance S, so HS of V is the vector okay. Again, take a vector V. It defines a unique geodesic, and so the geodesic flow moves the vector along this geodesic, but it also defines a unique stable horocycle or stable manifold as Frederick defined it, and it's a set of vectors which have the same endpoint at infinity. That's the stable manifold. And the Horocycle flow moves the vector V from a distance S for the Riemannian distance induced on the horocycle along this horosphere. Okay. That was just for notation. And a little exercise is that these flows are flows which act on the unit tangent bundle of the hyperbolic plane. But if you look at this identification, it's an exercise, and it's a simple exercise to show that the action of the geodesic flow on the unit tangent bundle corresponds to the right multiplication by diagonal matrices. So there were squares in the talks of Jean-François Quin, and that's the reason why you have a factor 1/2 here. Maybe he forgot some squares, but anyway, so, and the Horocycle flow acts by right multiplication by the unit potent matrices, like that. Okay. And then okay, bye. Now, if I want to speak about dynamical systems and the dynamical properties of these two flows, if I look at these two flows on the unit tangent bundle of the hyperbolic plane, I have nothing to say. I mean, all orbits go to infinity, and that's it. And so, as usual in math, when it's too easy, you have nothing to do. So the point is that one want to study the geodesic flow and the Horocycle flow on the unit tangent bundle of a hyperbolic surface. And so the hyperbolic surface, any hyperbolic surface can be written as a quotient of the hyperbolic plane by a discrete group of isometries. And the unit tangent bundle is a quotient of the unit tangent bundle of the hyperbolic plane by the action of gamma. And the point is that it's easy to see that the geodesic and horocycle flows commute with isometries. You can see it by looking at the picture, or you can also, if you did the exercise showing that geodesic and horocycle flow correspond to multiplication on the right by certain one parameters matrix flows, isometries act on the left, and so it commutes. So, but the geometric argument is enough, and so you have geodesic and horocycle flows acting on the unit tangent bundle of the hyperbolic surface. It's classical in dynamical system or in geometry to look at lattices or finite. So if gamma, saying that gamma is a lattice in PSL2R is equivalent to say that S has finite volume. And the typical example is when gamma is PSL2Z. So Jean-François showed you that it's a lattice and gave a bound on the volume, but you can check that a fundamental domain in the hyperbolic plane for the action of PSL2Z is this domain, and the quotient surface, which has some singular point, look like that. So it's a non-compact finite volume hyperbolic surface. If you prefer compact surfaces, there is a classical construction. For any integer g, at least 2, you construct a 4g gone with right angles. I will try. Okay. And then you identify them through a hyperbolic isometries like that. And it should give you a hyperbolic surface of genus G. Here on my picture, G equal 2, and here G equal 3, but and so it will give you compact surfaces. But I don't want to speak only about finite volume surfaces. There, you can also think to what is called Schottky groups. So you look at the hyperbolic plane or hyperbolic disk, and you look at isometries. Let's say an isometry, any hyperbolic isometry has 2 fixed points, hyperbolic isometry of the hyperbolic plane. And take an hyperbolic isometry A, which sends the complement of this disk inside this disk, and take another one which sends the complement of this disk into this disk. And if you look at the group generated by A and B, you can check that it's a free group, and the quotient surface is what is called a pair of pans. So something like that. That's S. And you can also do almost the same picture if you look at A, which is a hyperbolic isometry sending the complement of this disk inside this one, and B is like that. The quotient surface will be a punctured torus. So these are finitely generated groups where the quotient surface has infinite volume. And what other example I wanted to... Okay, there is a limit situation where when two of these disks can be tangent, for example, like that. So it means that there is a parabolic element which fixes this point, and a hyperbolic isometry sending the complement of this disk inside this disk. And if you look at the group generated by this, I'm not sure to succeed to do the good picture, but it should be something like that, with a finite volume end corresponding to this part, and to I'm sorry that I have never been able to do nice pictures. Something like that. So this one has, this surface has two types of ends. It has cusps, which are ends with finite volume, and it has what is called funnels, trompette in French, which has infinite volume. And so here you had just one end with finite, or finitely many ends with finite volume, and here no ends because the surface is compact. And I don't want to restrict the statements to such surfaces where all the fundamental groups here are finitely generated. You can assume that the group is infinitely generated. And for infinitely generated group, it becomes very difficult to do pictures, but the most simple picture corresponds to groups, to surfaces which are covers of compact surfaces. For example, think to a surface with infinite genus. So that are the kind of examples that I have in mind. And now, maybe the questions that one can ask, or the goal of the lectures. So it is to understand the dynamical properties of the geodesic flow and the horocycle flow. What does it mean, understand the dynamical properties? Depends on what you like. But for dynamical systems, you can ask if there are periodic orbits, if there are dense orbits, or if there are more complicated orbits, or if you, it is what I call topological dynamic. Not what I call, but what is called. And then you can speak about ergodic theory, so what concern invariant measures. So usually one considers invariant probability measures, but when one considers these geometric flows and the surface is not of finite volume, the natural measures will be infinite. So I will not restrict to the study of probability measures. And you can ask if there are several of these measures, if there is just one, if they are ergodic or mixing. And if there is just one measure, you have hopes that all orbits will be uniformly distributed to this measure, so it's called equidistribution. So all these questions make sense for any dynamical system. So the just a few general words for the picture of these two flows. The geodesic and horocycle flows, why will I study them together? Because every property of one flow is proven thanks to the properties of the other flow. They are really intimately related. The reason is the picture above on the right, the image of V by the horocycle flow is exactly the stable manifold of the vector V for the geodesic flow. So the orbit of V for the Horocycle flow. Yes, I repeat, but it's important. It's the only idea to understand. The Horocycle orbit for the Horocyclic flow of the vector V is exactly the set of vectors which have the same feature for the geodesic flow. That's the point. Everything comes from this picture. And so they are intimately related, but they have very different properties. The geodesic flow is a hyperbolic flow. Hyperbolic has several meanings, but you can see it in what is called the local product structure. Local product structure says that if you have two orbits, so two orbits here that are two geodesic, and that these two orbits have a vector with two vectors which are close at some point. If you have two orbits which come close together at some point, then you can glue the past of one orbit with the future of another orbit. That is called the local product structure. From the point of view of hyperbolic geometry, it's completely trivial. You take the geodesic coming from this point to this point, and it's clear that it has the same past than this vector and the same future than this vector. I insist on this property because it's really crucial. Saying that the past is independent of the future is something very strong in dynamical system. If some of you like symbolic dynamics, it's exactly what happens if you look at a full shift with finitely many symbols. You can take any sequence on the past, any sequence on the future, and if your shift is a full shift, you can glue them, and even if it's not a full shift but a subshift of finite type, you can glue them, and that's exactly what happens here. You can glue the past of the geodesic flow and the future. And this local product structure is the reason why the geodesic flow will be very chaotic. It will have entropy and mixing properties. And at the contrary, the same property of the geodesic flow will say you that all the horocycle should have the same behavior. Why? Because given any vector V with a determined future, so if you have a vector V which has a certain future, you can take any other vector W and glue the past of W with the future of V. It means that from everywhere or everywhere in your surface, you will find a vector, so anywhere, and close from any vector W with the same future than V. It means that horocycle orbits should be dense, because everywhere in the manifold, everywhere in the surface, you have vectors, let's say U, which have the same future than V, almost the same. So it exactly says that horocycles are dense. And okay, so maybe you could say that everything comes from the local product structure. I will go into more details during the lecture. So, but I will just repeat that the key property is that the horocycle orbit of a vector V is exactly the strong stable manifold for the geodesic flow of the vector V, that is, by definition, the set of vector W such that the distance from GTV to GTW goes to 0 when t goes to infinity. It's almost the same definition than Frederick. He looked at the distance between the base points, but in hyperbolic geometry is equivalent. Okay. Oops. Okay, so I will enter in the properties of topological dynamics. I will first mention a technical point. You have a discrete group, and this group is discrete. So if you look at the hyperbolic plane or hyperbolic disk, and you look at any point, for example, the center of the disk, but it has no importance, and you look at the orbit of this point. As the group is discrete, it has no accumulation point inside, and all accumulation points of this orbit are in the boundary. So it's what is called the limit set. The limit set is exactly the set of accumulation point of any orbit. As the group acts by isometries, it does not depend on x0. And the fact is that we will assume, even if I will not mention it in the sequel, but we will always assume that gamma is what is called non-elementary, which is equivalent to say that the limit set is infinite. It's also a closed invariant set. It's a minimal closed invariant set for the action of gamma on the circle, but I'll not mention. And Frederick explained you the Hopf coordinates, but so if you take a vector v in the unit tangent bundle of the hyperbolic disk, and you look at it geodesic, and it's important to consider the negative and positive endpoints of these geodesics. And he said you that the unique tangent bundle of the hyperbolic plane is homomorphic to the boundary. Here it's the circle times the boundary minus the diagonal times R. And in fact, when you have any non-elementary discrete group, you have to restrict the study to good vectors. What are good vectors? In fact, the dynamics of the geodesic flow is interesting on what is called the non-wandering set. And the non-wandering set is exactly the set of vector on unit tangent bundle of the surface, which have a lift on the unit tangent bundle of the hyperbolic plane such that v plus and v minus are in the limit set. The limit set carries a lot of information, and you have to restrict the study to the vectors which point inside the limit set, positively and negatively. So any statement that I will do on the geodesic flow, even if I don't, even if I forget to precise it, it will hold on the non-wandering set. If you don't want to care about these details, it's not a detail, in fact. If you imagine that the surface has finite volume, it's everything. When you have a lattice, finite volume or co-compact, the limit set is everything. So maybe I can mention it. If gamma is a lattice, the limit set is everything. But also, if gamma is a normal subgroup of a co-compact lattice, for example, in this picture, the limit set is also everything. The point is that, okay, that's a good set for the geodesic flow, but this set is not invariant by the horocyclic flow. You have the limit set is a counter set. And if you look at the vector v, which is in this good non-wandering set, and if you look at this, its horocyclic orbit, you will of course find vectors w on the horocycle of v, such that negatively you are not in the limit set. So the non-wandering set of the horocycle flow is exactly the set of horocycles which cross this set omega. So it's exactly the set of vectors which have a lift such that the positive endpoint is in the limit set. Okay, so all the statements I will do on geodesic and horocycle flows, even if I forget to mention it, the geodesic flow lives on omega and the horocycle flow on E. And of course, if gamma is a lattice, these sets coincide with the full unit tangent bundle. Okay, now, so I come back to this question of topological dynamics. I would like to present you some statements and arguments which I find interesting to understand the relation between the two flows. So my aim is not to be exhaustive in all the important properties of these flows, because they are studied. Maybe I could mention it. The first results, in fact, these two flows were very much studied at the birth of ergodic theory in the 30s by Hopf and Edlund. They were with the symbolic dynamics on shifts. Were the most natural examples to do ergodic theory. So results are very old, and since the 30s, a lot of results were proven. But so I will also not follow the historical progression of results, and I will begin with a result of Eberlein. I will write theorem because I find it very important, but in fact it's not difficult at all, which says that the horocycle orbit of a vector v is dense, so of course in E, if only if the geodesic GTV for T positive is not quasi-minimizing. What does it mean? A vector, a geodesic, so that's a definition. A geodesic GTV is quasi-minimizing if there exists some constant such that for all positive t, the distance between v and GTV is at least t minus constant. Think to the hyperbolic plane when there is no group acting, the distance between v and GTV. I should speak about distance of base points, but it's not very important. In the hyperbolic plane, the distance between v and GTV is exactly t. So, but of course, on a compact surface, the distance between v and GTV is bounded. And as the geodesic flow is the geodesic flow, this thing is always less than t. But saying that this is at least t minus constant, it means that up to a mistake at the beginning, the geodesic GTV goes to infinity at maximal speed. So it's not possible on compact surfaces. If you have a finite volume surface, it's possible if the geodesic goes up to the cusp. If you have funnels, it's possible if you go to the funnel or to the cusp. And in this example, you have quasi-minimizing vectors going straight away to infinity and in the other direction. There is another formulation of this property. Maybe I should say proposition, but that the horocycle V is dense if and only if you look at V plus V plus, which is in a priori, it's a point of the limit set. The horocycle is dense if and only if this point is horospherical. Is a horospherical limit point. In fact, what is the definition of horospherical limit point? There are two kinds of limit points which are very useful, which are radial limit point or conical limit point and horospherical limit point. So a point is in a limit set if it is the limit of a sequence of points of the orbit of x0. But a point is radial if there is a sequence of points of the orbit which stay at bounded distance of a geodesic ray. So here, Xi is a radial limit point. In some references, it's written conical, but it's the same. So it means there are infinitely many points converging to Xi at bounded distance of a geodesic ray. And a point is horospherical. It's a little bit weaker. It says that given any horosphere, horocycle centered at Xi, so as small as you want, there will always be points of the orbit inside. And in fact, these two propositions or two theorems say that you can understand if a horocycle orbit is dense in terms of the geodesic orbit or the action of the group on the boundary. That's why these results are important. And it's just a remark. It's an exercise to show that saying that V plus is a radial limit point is equivalent to say that the geodesic flow, the geodesic orbit of V, when t goes to infinity, returns infinitely often in a compact set. And you see certainly on the picture that being a radial limit point is stronger than being a horospherical limit point. And so, in particular, you have, for example, if V is periodic for the geodesic flow, is much stronger than saying that it's stronger than saying that V plus is a radial limit point. And it's much stronger than saying that the horocycle orbit of V is dense. So that's a consequence. Now I have to manage with these blackboards. Soit. Ah, c'est classe. Okay. Another result that I find very important to understand the relation between... ah oui. Another result that I find very important is the following result. The geodesic flow is topologically mixing on omega is equivalent. I will give the definition, just it's okay. Radial limit point, do you see the picture? It's a point of the limit set, which is a limit of points of the orbit of x0, which converge to psi along a geodesic ray. So radially. No, because it's an isometry. It's a group of isometry. So take another point, and it will change the distance to the geodesic ray, but it will not change that you converge, staying at bounded distance of a geodesic ray. It just changes the distance to the ray. So I will state the theorem before the definitions. It's not good, but it's like that. So the geodesic flow is topologically mixing is equivalent to saying that there exists a vector V with a dense horocycle. And it's also equivalent to say that the length spectrum of the geodesic flow is non-arithmetic. So I will give the definition in 1 second. Just I would like to mention that stating this theorem like that for hyperbolic surfaces, it could seem a little bit strange because there is a result saying that if S is a hyperbolic surface, then the length spectrum is non-arithmetic. So in fact, as I speak only about hyperbolic surfaces, all these conditions are true. But the reason why I state it like that is that the equivalence between these three sentences are given by arguments which are much more general than for hyperbolic surfaces. And maybe I should state names. Saying like that this one should be due to Françoise Dalbeau, and this one should be due to several persons, maybe, of course, Edlund, but also Eberlein and Françoise Dalbeau. But the arguments I will give you are a lot of them were written by Yves Couden. Okay, so I will try to give you some of the arguments for these. Where is the other? I have to give you some definition first. What is topologically mixing? So the definition, GT is topologically mixing if for all A and B open sets in omega, so you take A and B, after a while there will always be vectors of A centered in B. So for T large enough, and for all T large enough, GTA intersects B. So the fact that in the future you will enter in B does not depend on the fact that you were in A. Or not. What? This second sentence is clear. And what is the length spectrum? Okay, if gamma is an element of the group which is hyperbolic, it means that I should say, if gamma is hyperbolic, it has two fixed point on the boundary, and it acts by translation on the geodesic joining gamma minus and gamma plus, and so it induces on the quotient a periodic geodesic. And this periodic geodesic has a length, which is the translation length of gamma. The translation length of gamma acting on this geodesic is exactly the length of the periodic orbit of the geodesic flow, at least for simple geodesics. And saying that the length spectrum is non-arithmetic is it means that you look at all the lengths of this periodic orbit. There are real numbers, and you look at the group generated by these lengths. So it's an additive subgroup of R. And if it's a non-arithmetic, if this subgroup, you of course know that all subgroups of R are either closed or dense, and then what? And so saying that the length spectrum is non-arithmetic means that the group generated by the length is dense in R. Okay. So I. Et là, je peux y arriver. So I will try to give you some arguments, not all that I plan to give, but the key point is that comes from the basic properties. Basic means it's not a good word, maybe. We will use three very fundamental properties of the geodesic flow. The first, I already mentioned it, is the local product structure. Take two vectors which are close one to the other. It's possible to glue the past of V and the future of W. So that's the local product. That's the first important property. The second very important property is the Anosov closing lemma. What says the Anosov closing lemma? This lemma says it's not a lemma, it's a theorem. But it says that if you have a geodesic which is almost closed, then there exists a periodic geodesic which is closed and which has almost the same length. I don't want, as I go slower than I thought, I don't want to write you the precise quantifiers, but you need to, okay, well, anyway, the picture is enough. For any vector which such that for t large enough GTV is close to V, then there exists a vector V T epsilon, which is periodic, which is close to V, and which has period almost T, up to some epsilon. And the third very important property is called the transitivity. Transitivity says that if you have A and B open sets, you can go from A to B, and you can go infinitely often. So for all T, you have all large T, you have T larger, small t larger than T, such that GTA intersects B. It's in general, it's much weaker than the property of mixing. That's the reason why you should always be careful with the order of quantifiers in mathematics. It's much weaker, but it's still very important. It says that you can go from everywhere to everywhere. Of course, I never mentioned that my hyperbolic surfaces were connected, but if you want to be rigorous, the geodesic flow is transitive if the surface is connected. Okay, there exists a vector which is sometimes denoted like that, such that U belongs in the strong stable manifold of V. That means exactly that it has the same feature. And so it is a flow. So if it would be just a discrete dynamical system, the local product structure for hyperbolic diffeomorphism would say that U belongs to the strong unstable manifold of W. But for a geodesic flow, you have the direction of the flow, which can do a slight mistake. So it belongs to the strong unstable manifold of not almost W, but maybe it's a G sigma of W with some sigma, which is very small. And also, U is at small distance from V on the strong stable manifold and small distance from G sigma of W on the strong unstable manifold. It's what does mean glue the past and the future. Thanks for the question. Okay, so all the properties, I will not prove everything in these results of Eberlein, Edlund, etc. But I would like to show you few implications using these three properties. So the unit tangent bundle of a hyperbolic. I will begin maybe with the fact that, some proofs. I wrote some informal notes where I wrote the arguments of these results, which are mainly due to the result, not the result, but the proofs are mainly due to Ifkuden. But I wrote them again, so you can see the missing proofs on my webpage, on the notes. Maybe on the website of the conference also. So let's say I will prove that the mixing implies the non-arithmeticity of the length spectrum. That's very difficult. Take an open set U. The mixing property says that there exists some T, such that for all T larger than T, GTU intersect U. Now assume that U is small. I don't give you precise quantifiers, but small enough so that the conclusion of the closing lemma is true. So for all T large enough, you have GTU intersect U. It means that there exists a vector U, UT in U, such that GTUT come back in U. But as U, if you choose it small enough, it means that GTUT is very close from UT. So it means that there is a periodic orbit. Okay. So what a little bit more difficult. I'll try. Please don't ask me some details, but I will give you the idea about the fact that non-arithmeticity implies mixing. Okay, so maybe I was fast. Sorry. So the closing lemma, the small enough means that you can apply the closing lemma, gives you a periodic orbit, P like periodic, of length t plus minus epsilon. So it means that the set of periodic orbits is epsilon dense in R, but epsilon was arbitrary. So why non-arithmeticity implies mixing? First, that is an exercise. There are exercises of different difficulties. This is not too difficult using transitivity. That it's enough. Where is the definition of mixing? For the mixing, you want to be able to go from any open set A to any open set B in any time large enough. But it's enough to take A equal B. Then if you have B different to A, you use transitivity to go from B to A, and then mixing to go from, okay. And local product to glue pieces of orbits. So take any open set. And maybe I never mentioned that the periodic vectors for the geodesic flow are dense in the non-wandering set of the geodesic flow. That's a very important fact. So if you take an open set, as periodic vectors are dense, there is a periodic vector inside. So it's periodic. And as the length spectrum is non-arithmetic, if you fix some arbitrary epsilon, there exists some other periodic orbit somewhere. So there exists a p prime periodic, and also integers n, m, such that n times the length of p minus m times the length of p prime is less than epsilon. And then I will just give a picture, not give the details. You use transitivity in a small neighborhood of p and in a small neighborhood of p prime to find an orbit going from p to p prime. That's transitivity. This one is fixed. It has length, let's say, C1. And you can find another orbit which goes from p prime to p. This one is also fixed. It has length C2. And then you will turn around the periodic orbits as long as necessary. So you go from the negative path of p, and then, so by the local product structure, you glue the path of p with this piece of orbit. So you arrive here, and then you will glue it with a piece of orbit of p prime, and you will turn, you will do k times m turns. So it's a multiple of m. And then, I don't remember where you are, but then by local product structure, you come back. And then by local product structure, you glue it with the future of p. Okay? So for what I did is that for all k integer, let's say greater than 1, but it has no importance, I construct an orbit which is negatively and positively asymptotic to the orbit of p. And now it's an exercise counting lengths, epsilons, using non-arithmeticity. If I do it on the blackboard, I'm sure to be wrong. That on this yellow orbit, there will be some vector somewhere in the very close to P, such that, so for all k, there will be a vector vk very close from P, and such that g tk of vk is very close from P also, because we return back to this point, and such that tk, the set of tk for all k greater than 1 is epsilon dense in some interval. No, what I did want. I want to prove. No, that's it. I wanted mixing. So that's okay. Yes, I wanted to prove that non-arithmeticity implies mixing. So I used non-arithmeticity to produce these. For the moment, non-arithmeticity is hidden, but that's in the exercise. That why? Yes, because you want. Okay. In the mixing property, you want that for all t large enough, you come back in A. But the geodesic flow is continuous. So if A is an open set. So for epsilon small enough, it's enough to prove that the set of times where you come back is epsilon dense. Because by continuity, it will be an interval. And then, so you check, so that is the exercise that I don't want to do, that the set of tk is epsilon dense in some interval t0 plus infinity, and use the continuity of the geodesic flow to conclude that you have all times. Maybe it's a little bit fast, but writing the details is not enlightening. If you just have to think about this picture. But what? Of course, it's going much slower than I thought. Maybe another property. I will show you that topological mixing implies that there is a dense horocycle. What? Where? Let's see. So how does it work? Take U, which is any open set, and take P, which is a periodic vector. Periodic vectors are good because they come back. Oh, that's tautological, but I would like to try to find some vector in HS of P, in the horocycle, strong stable horocycle of P, which enters in U. It will say me, as U is any open set, it will say me that the horocycle of P is dense. So Okay, but take a very small neighborhood of P. And by mixing, so the mixing says me that for all t large enough, there exists a vector ut in U, such that gt ut is in my neighborhood V of P. Okay? And so it's here. Okay? But now, always the same game, I can use the local product structure and glue my gt ut with the orbit of P. And so I get an orbit which has the same path. In fact, I glue the path of this vector gt ut with the future of P. It gives me an orbit which has the same future than the periodic orbit and which has the same path, etc. So it arrives here, very close from ut. And as U is open, it comes, I get a vector WT. So WT is a vector which is in U, such that GT WT is close to P. And now observe that it's true for all t large enough. And the fact is that GTWT is close to P, but it's also in the stable horocycle of P. Okay, but P is periodic. So I can choose T as a large multiple of the length of the periodic orbit. So that WT, it's G minus T of GT WT. But as P is periodic, if you are in the stable manifold of P, if you look at G minus L of P, G minus L of P is equal to P because P is periodic. That's a stupid remark, but that says that WT is in the strong stable manifold of G minus, I choose T as a multiple of the length of P. So it says me that my WT is in the strong stable manifold of minus KL of P, which is P. So it says me that I found in U a vector of the strong stable manifold of P. That's what I wanted. Maybe I wanted to prove more, but I also wanted to concentrate the main part of my lectures on the ergodic theoretical properties of these flows. So I will stop here. And the other things that I didn't prove, in particular, are the Eberlein properties and the missing implication use the same kind of arguments. Saying that, okay, I want to prove that there exists some vector whose horocycle is dense. I will choose it to be a periodic vector. So I fix a periodic vector. I want to prove that its horocycle is dense. Saying that it's dense, it's exactly the same thing than saying that given any open set, I can find a vector in the horocycle which enters. That's the density. Okay, and so I try to construct a vector in the strong stable manifold of P, which is in U. And in fact, it's exactly what I did. Any. And in fact, it's something that I mentioned without proving it because I didn't prove the Eberlein property, but it should be somewhere. when you have okay, I didn't prove it, but what I wrote above is that if you have a vector which is periodic, then its limit point in the boundary is radial, and then in particular it's horospherical, and then it means that the horocycle is dense. So I didn't prove it, but it's true. What I proved is that here it proves more than. You're right, I proved more than what I wrote. I proved that if the geodesic flow is topologically mixing, then all periodic orbits for the geodesic flow have dense horocycle. Okay. Yes, so now I wanted to speak about ergodic theory. And so about invariant measures. Okay. Maybe it's too. Comment il s'appelle lui? So now I will speak about the ergodic theory of these two flows. And for doing that, I will need the Hopf coordinates, but there are two ways to define some Hopf coordinates. And from the point of view of the stable foliation, I will prefer a slightly different Hopf coordinate than the one of Frederick. So if you have a vector v on the unit tangent bundle of the hyperbolic plane, you take v minus and v plus, which will give you, say you on which geodesic you are, and you need a real parameter to know where is v on the geodesic that it defines. And you have the origin of the disk somewhere, x0, and Frederick said that you can look at the distance between the projection of x0 on the geodesic and the base point P of v with a sign. I have a problem with signs, so I will not give you the sign. But there is another way to, which is equivalent, to give a homeomorphism between the unit tangent bundle of the hyperbolic plane and the boundary times the boundary minus the diagonal times r, which is the following. For a vector v, I associate v minus, v plus, and the Boozman cocycle, the distance. Okay. That should be the good sign. That can be thought as the distance from x0 to v plus minus the distance from p of v to v plus. Of course, this has no meaning because it's infinity minus infinity, but it's a good intuition for it. And so it's not exactly the same, but the advantage is that the strong stable manifold of v for the geodesic flow in this coordinate is exactly the set of vector w such that w plus equal v plus, and let's say that I will call tau of v the real coordinate on the geodesic. So by definition of horospheres, tau of w is equal to tau of v exactly when the Boozman function is constant. That's a definition. Okay, it has no importance because if you look at the dt measure on the real coordinate that it defines, it will be the same than the dt coordinates given by the other convention of Hopf coordinates. So from the point of view of the homeomorphism is different, but from the point of view of invariant measures, it has no importance. Okay. Now I would like to do a remark which was used by Frédéric, but I will say it again. If the unit tangent bundle of the surface is the quotient of the boundary times the boundary minus the diagonal times R by the group. And so if you have a measure M, measure on T1S, which is GT invariant, it's the same that having, I look only I consider only radon measure. I don't want to consider finite measures because it's too restricted. So consider radon measure on the unit tangent bundle of the surface, which is GT invariant, is the same that radon measure on the unit tangent bundle of the hyperbolic plane, which is not only GT invariant, but also invariant by the group, because I lifted it. And as the geodesic flow on these coordinates, the geodesic flow acts by translation on R. So saying that a measure is invariant by the geodesic flow is exactly the same than saying that M tilde can be written as a measure mu times dt, where mu is a radon measure, which is gamma invariant on the boundary times the boundary. And when I speak about the geodesic flow, in fact, I should consider only measure on omega, and it's here you replace T1H by omega tilde, and mu is a measure on the limit set times the limit set. And if you want to consider measure invariant by the horocyclic flow, that's strange. If I look at a measure which is invariant by the horocyclic flow, oh no. So on the non-wandering set of the horocyclic flow, it's the same than considering its lift to the unit tangent bundle or to the lift of the non-wandering set, E tilde, which is HS invariant. And if you look what in the Hopf coordinates, saying that what is a horocycle orbit? If you have a vector V, I just wrote it here. The horocycle orbit is the set of vectors W, which have the same positive coordinate, the same real parameter, and another negative endpoint. Okay, that's exactly what I wrote here. But then, what does it mean to have a measure which is invariant under the horocyclic flow? It means that here, along this horocycle, the measure is the ds. It's the Lebesgue measure on the horocycle. So it's equivalent to say that M tilde can be written as, let's say, rho times, I would like not to write it exactly like a product, but locally, if you imagine you have a vector V, you have its horocycle orbit, HS of V, and the horocycle is parameterized. What is a horocycle? Saying in which horocycle you are is exactly the same than saying giving a V plus and tau of V. If you give a coordinate, a positive coordinate in the circle and a real parameter, it's the same than giving a horocycle. So here you have the space of horocycle that is identified to the circle times R. And if you want a measure which is invariant by the horocyclic flow, it's exactly the same than saying that you will have a measure on the circle times R, and along the horocycle you will have ds. So it's, let's say, rho times ds, where ds is the Lebesgue measure on hs of v, and rho is a gamma invariant measure on the limit set times R. And when you want to study the ergodic theory of these flows, you always do this game. In fact, many things are done by considering the boundary. I have a few minutes left to give some more definition, and I will I'm not completely sure that the definition of ergodic measure was given, but I will just recall it, not write it. A measure is ergodic if there are no non-trivial invariant sets. If the measure is finite, the usual way is to say that any invariant set has measure 0 or 1. If the measure is infinite, it's better to say that any invariant set has measure 0 or its complement has measure 0. So the notion makes perfectly sense. A mixing measure, what is a mixing measure? It's a measure with respect to which the past and the future are independent. So for all R, A and B Borel sets, the measure of A intersected with GTB goes to mu of A, mu of B. This definition makes sense for infinite measures, but it's not so interesting. If you think to an invariant probability measures, it exactly means that you can write it like that, and so you can see it as a condition that to the fact to be in A, the probability to go to B after times t becomes independent to the fact to have been in A. Okay, it's exactly in probability. It's exactly the same. Okay, it will exactly say that A, when t goes to infinity, the fact to be in A and the fact to be in GTB are independent. So the past and the future are independent. Yes, okay. And now I said that for all the topological properties that I proved, I made no assumption on the group, except that it's non-elementary. But if you want to do ergodic theory, okay, there are some general results on invariant measures which can be proven on general hyperbolic surface, but it becomes difficult and not so interesting. So for a while I will... Wait, there is a question? No. So for a while I will assume that the surface has finite volume. And so there is a very natural measure. So we saw that the unit tangent bundle of S is a quotient of PSL2R by the group gamma. And in the talk of Jean-François Quin, you learned about the Haar measure of PSL2R, which is left and right invariant because the group is unimodular. And so the fact that the Haar measure is left invariant, if you look at the left Haar measure, it induces a measure which is well defined on the quotient. But the fact that it's right invariant will give you a measure which is invariant under the right multiplication by anything, and so in particular by the geodesic and the horocyclic flow. So you can look at the Haar measure, but if you don't like the point of view of Lie groups, you can think to the Liouville measure. So if you have coordinates, you have a vector v based at a point x plus y, iy. The Haar measure, if you have an angle theta, it's just dx dy over y square times d theta up to normalization. And in other words, it's a Riemannian measure on the unit tangent bundle of the hyperbolic surface S. It's a Riemannian surface, and it has a Riemannian natural measure. And the point is that, okay, I will stop in less than 5 minutes, but I will not now. Okay. The very important point from the point of view of Hopf coordinates is that this measure, I will call it L. So if you look at, or L tilde, L like Liouville or Lebesgue, not R. But if you look at L tilde on the unit tangent bundle of the hyperbolic plane, locally, it can be written as a product measure. The measure is equivalent to it's equivalent to the Lebesgue measure on the circle times the Lebesgue measure on the circle times the Lebesgue measure on R. And there is a density here. I don't want to write it, but it's a formula similar to those formula that Frédéric wrote for the Bowen-Margulis measure. The point is that what is important is that it has this product structure. And it's not a trivial fact at the first. I mean, the homeomorphism given by the Hopf coordinates has no reason and is not in general absolutely continuous. And so the image of the Lebesgue measure on T1H on this product has no reason to be absolutely continuous to the product of the Lebesgue measures. But in fact, it's true. And it's due to Hopf in dimension 2 in the 30s. And it's due to Anosov and Sinai in the, I don't know, 70s, 60s, 50s. Okay, so Sinai had the Abel Prize, so it's a good day to. So I think it's independent. They proved it independently. So okay. So in the Hopf coordinates, the Lebesgue measure has a product structure, and it's really a key point. You saw that from the topological point of view, the local product structure was very important. And from the ergodic theory point of view, it's also extremely important. And tomorrow, no, this afternoon, we will deduce a lot of ergodic properties. This measure is, maybe I could just finish with this. This measure is so GT and HS invariant. It is ergodic for the action of the geodesic flow. From this ergodicity, one can deduce that it is ergodic for the action of the horocyclical flow. From this, one can deduce that it is mixing for the action of the geodesic flow. And from this, one can deduce that it is a unique HS invariant measure. And then from this one can deduce that, no, finite volume. Ah, okay. Yes, they are periodic. So except periodic measure. Unique ones. Unique invariant ergodic. To give okay. So it's the unique. It's essentially the unique interesting ergodic invariant measure. That's a true statement, even if it has no definition. And from this unique ergodicity result, one can deduce that all non-periodic all non-periodic orbits are equidistributed. And so I will try to give the main proofs of all these implications, and maybe if I have time to speak about the geometrically finite case. Thank you.
First, could you recall me what it means being elementary for the group?
The limit set does not appear anymore. You take a group. It's a discrete group, so you take any orbit. It accumulates somewhere, but not inside. It accumulates on the boundary, on a set which is called the limit set. And non-elementary means that this set is infinite.
Okay. Secondly, and it's not related with that, in the proof that non-arithmetic implies mixing, I think the choice of all things and the orbits depends on epsilon. How do you ensure that your time when the epsilon dense orbit is inside of your set don't grows without bound for ensure the mixing?
In fact, when you use the local product structure, for example, gluing the past of P with this red orbit going from a neighborhood of P to a neighborhood of P prime, you get a vector which is in the strong stable manifold of P, and a strong and stable manifold of a strong stable manifold of this red orbit, the strong and stable manifold of P, up to a slight translation along the geodesic. But it is quantified. So you know that this vector is at bounded distance, very small, let's say epsilon over 1,000, on this stable and unstable direction. And so then you glue here, and you will also lose a few epsilon. But for this yellow, for all k, I glue just finitely many orbits. The past of P, the red orbit, a piece of P prime, the other red orbit, and then the future of P. So 1, 2, 3, 4, maybe I glue 4 or 5 times. So I glue finitely many times pieces of orbits of lengths which grow with k. But the epsilons, you have 5 times epsilon. And so it's controlled.
Any more questions? Okay, then let's thank the speaker again.